I will return your test. The tests are graded. I did post the grades, but that was sometime like at 1 o'clock this afternoon, so I didn't send an email or make an announcement, but the grades are posted, but I'm going to give you your grade. And I just posted the answers about 15 minutes before class, so if you go to the Blackboard page, the answers are posted as well, all right, to the exam. So your grade is updated. The flux totals are updated except for maybe those people who went to SI last week. I haven't seen that print out yet. So that's not in there. I'll get that, I think, tomorrow. So I will adjust that. All right, so Brittany, is Brittany here? Mason. Mason. Valerie. Eldrin, I think, sits right there. Chris. Jessica Hernandez. Is Jessica Hernandez? Anissa. You're Anissa. Yeah, I know people's names not as well here since Taylor's been passing out papers. Dylan. John. Wally. John. Mario. Daniel. Garzon. Are you Garzon? Okay. Faria. Is Faria here? Don't see. Emily Hernandez. Mafruha. Where does Mafruha sit? Astrid? Is Astrid here? I don't see Ira either. Daniel Navia. Ah, you're Daniel Navia. Okay. Ryan. I guess that is yours. Scratch paper. Mariah. Mariah usually sits up here. Jennifer Herrera. Cecil. How do you do? Miguel. Ray. Who is Ray? Hyder. I know. Okay. All right. Anybody who's supposed to get one did not get one? Which one are you?
I am Raj.
You are Raj. I just called your name.
Awesome, thank you.
Raj, okay. All right. Okay. I do not know where Taylor has escaped to tonight. All right, so the scores were fairly similar to test number 1 in general. Some people did quite a bit better, though, so that's encouraging. So your total score, right, has been updated, so you sort of know pretty much where you stand at this particular instance. If you look on WebAssign, 2 things about the test now that I've got to warn you about, though. Okay, there were some instances, maybe less than on the first test, but some instances where I did not see enough work. So there was very abbreviated in terms of the work. But these problems are very complex, okay? So they typically require some detail, okay? It took me a long time to grade them. So if I am seeing major skip steps, I am going to be suspicious of where that answer came from, okay? So you have got to be careful about indicating your work. Sometimes I took off points for that, and sometimes I did not, all right? But I still may have made a note that I'm not seeing steps here that I think should be there, all right? Now, that brings me to point number 2, okay? I teach this course frequently, so therefore, it's possible that you have seen test number 2 from me floating around, okay, from past semesters. I got the impression that I had seen that in the work on the test. So some people had gotten hold of a prior test and had somehow memorized the answers from that prior test, all right? That is a losing strategy, okay, because I can easily adjust for that, all right? The strategy to get out of Calculus 2, to pass Calculus 2, is to practice and learn and prepare. That's the same strategy for doing anything in life, okay? So if you are in that boat of having seen prior tests, okay, better think again about the use of those prior tests, okay? Because on test number 3 now, that's not going anywhere. And I know you have not seen a final exam. That I know you have not seen. So that cannot help you on the final exam, all right? So what you need to do is prepare, okay? The people who, now this was very evident in general, but almost specifically in particular, the people who went to the Math Center, who I know then were preparing, okay, or the people who went to Taylor's session, who I know were preparing, did as well as they did on the first test, or did significantly better on test number 2, okay? So that is the winning strategy, all right, okay? That's the winning strategy for passing Calculus 2. So be aware of that, all right, okay? I know you know that as students, but it's very tempting to take shortcuts, okay, and to think, oh, I'm being clever, okay? I pulled one over on the professor, my Calculus 2 professor, and that's rarely the case, all right? That's rarely going to be the case. So not just for me, but for any professor, all right? That will become apparent quickly. Yeah. Yeah, the answers are, I just posted them right before I came in, okay? So they are there, all right? All right, so there's Taylor's session, next session, okay? Thursday, all right? And this will be a ripe opportunity to, this week will be a ripe opportunity to go to Taylor's session because, Taylor, you're going to talk about trig substitution? You cannot really get enough practice with trig substitution. Oh, 0 attendance, okay. Yeah, so more partial fractions then, because I moved the due date back a little bit, so you've still got time to work on partial fractions. We still have a couple of examples to do with partial fractions, more of the more complicated examples that I didn't get to before the test, so we're going to look at those, and then we're going to dive into trig substitution, and that's going to be not one of the intellectual high points of the course, but maybe one of the more challenging homeworks, okay? For the class, all right? Okay. All right, so that's kind of where we're at. So let me show you the last 2 examples from partial fractions, because if you have questions from partial fractions, I think they probably are similar to these examples, which I did not get to. If you have any more questions about the test, in particular how your test was graded, then you can always see me separately, right? Okay, to ask about that. Okay. But in general, the test median was above 70, so that's good. Okay. It doesn't always happen in Calculus 2 to have test median score. That means half the scores were above and half the scores were below. But to have a median score in the 70s doesn't always happen on Calculus 2 tests. So if you're one of the happy ones above the median, then you got to keep up that preparation, right? Okay. This is not what I want. Into test 3. Oh, that reminds me about test 3 now. So this is the same situation across the university. The schedule is really odd this year because we started so early in August and Thanksgiving falls so late. So the last class day is actually the Tuesday before Thanksgiving. So please do not make plans to not be here the Tuesday before Thanksgiving because the last test will be on that day, okay? And I'm not making exceptions for that. So that's the last class day, and so that's the last time we have to give the third test. And then the final exam is sometime after that. It's probably several days after that. It may be like 10 days or 2 weeks. It's not? Oh, so it's the following week. Okay, well, all right. So I thought maybe it might be the week after the last test, but it's on the 5th. That's actually better, okay, because that gives you less time to forget stuff, all right, before the final exam. But anyway, so on the 26th, 3 weeks from today is the last test, okay? So we have a tight schedule between now and that last class day. So it's really important that you come to class. I can't stress that too much. You really need to come to class between now and then, okay? So I know sometimes things are busy and it's late in the day and so it's tiring, but you really got to make an effort to come to class. But if you miss class, you know, if you just absolutely have to miss class, then you've got to watch the video. I mean, you're just going to have to force yourself to watch the whole video, okay? Because there's really nothing you can sacrifice between now and the third test, okay? All right. Okay, so, wow, all right, so this one looks tough, okay? So that's kind of an impressive irrational expression there that we want to integrate, okay? And it looks like kind of a perfect setup for using partial fractions, right? Because the degree of the bottom is bigger than the degree of the top, okay? And I don't think we can do this by substitution. That would really be a miracle if we can integrate that one by substitution. You might have an inkling that we can integrate by substitution because if you take the derivative of the denominator, right, you're going to get 3x squared plus 4x plus 1, which kind of looks like the numerator, correct, but the coefficients are so far off that I don't think integration by substitution is going to be useful, right? Okay. Remember, if you had a denominator and then the derivative of the denominator is in the numerator, you can perhaps integrate that using natural log, okay? Using integration by substitution and then natural log. But it looks like we're not going to quite make it in this case. Using substitution. Oh, by the way, that reminds me for a problem on the test, okay? So you don't want to forget just your plain integration by substitution. And so that's 1G. That was an integration by substitution problem. That does not require integration by parts, okay? So some people recognize that you could integrate by substitution, but some people were so obsessed by that point on the test with integration by parts, so they were trying to do it with integration by parts, but you can't do that really very well with integration by parts, but it just requires substitution. Okay, well, this one, though, is the opposite case. I don't think we can do this with substitution, so we're going to try using partial fractions, but that does require that we be able to factor the denominator. If we can't factor the denominator, we're not going to get anywhere with not integration by parts, but integration with partial fractions, right? So, but fortunately here, the denominator does integrate for, does factor for us, okay? So, so the denominator factors by first factoring out x. Let's do that separately so I don't waste too much space here. So for the denominator, first we can factor out an x. So that would give us x squared plus 2x plus 1, right? Okay. And then, of course, that factors as x plus 1 times itself, right? X plus 1 times x plus 1. So the denominator factors really nicely there. That x plus 1 times x plus 1, though, I want to write that as x plus 1 squared, okay? Of course, it is x plus 1 squared, but I want to write it explicitly as x plus 1 squared for a reason. And that has to do with the partial fraction decomposition of this expression, okay? All right. So So you know now, right? You're going to break this up, okay, as you're going to break this up as the sum of fractions with smaller denominators, right? Okay, and so so we're going to rewrite that integrand, right, as the sum of some fractions with smaller denominators, okay? But here's the denominators you're going to have to use, okay? They are going to involve the factors here, right, of this denominator, okay, so x and x plus 1. So you're going to write one fraction with a denominator of x, okay? But now I want you to notice this is a factor that's squared, okay? So when you're doing partial fraction decomposition of fractions and you have a factor that's squared, you're going to have to repeat that factor. Otherwise, you're not going to get the proper partial fraction decomposition. So I have to actually end up with 3 terms here in my integrand. Okay, well, that's not that great because now I've got 3 terms, right? But nevertheless, that's the only way to get the appropriate partial fraction decomposition. So for one of those fractions, you're going to have denominator of x, right? For the second one, you will have denominator of x plus 1. And then for the third one, you're going to have x plus 1 squared, okay? Since x plus 1 is squared, you're going to have to repeat that factor once to the first power, x plus 1 to the first power, and then x plus 1 squared. Of course, what is the least common denominator of these 3 fractions? It is x times x plus 1 squared, okay? But notice you have this, this possible fraction in the partial fraction decomposition, all right? Now, for the numerators there, well, we don't know what those numerators are, right? So we're just going to have to give them variable names. So let's call this one A, and let's call this one B, and then this one, of course, let's just label it C, all right? Just write down some variables alphabetically there. And so I have to figure out what A, B, and C are, correct? Now, I think, though, that once I figure out what A, B, and C are, I'm going to be pretty happy, right? Because, then we're going to break this up into 3 integrals, and I think I'll be able to integrate all 3 of those things, right? This one, I can integrate using what? Natural log. This I can integrate using what? Natural log again, right? Because the derivative here is just going to be 1, okay? Right? Okay? And of course, you'll be able to factor the b out in front of the integrand, so you'll have 1 in the numerator here. So you're going to be able to factor this using natural log. This is not going to factor, though, using natural log. How are we going to factor that one? Well, with substitution and then the anti-power rule, right? So this one you can integrate using the anti-power rule. Oh, y'all are getting good, okay? All right, so that is great. So that's a consequence, I think, of I can feel of going to tutoring. Okay. All right. Now, but we got to figure out what the A, B, and C are, right? So that's really kind of the hard work here in the problem, other than recognizing that our partial fraction decomposition may look like this. All right. So I got to figure out what A, B, and C are. Okay, so now, so here we have to pretend, right, that we're going to add these fractions back together. We're not really going to add them back together, right, but we have to do that off to the side so we can figure out what the appropriate values for A, B, and C are. So let's see, when you add those fractions back together, you're going to have to build up the denominator of this fraction, right, by multiplying by what? No, just x plus 1 squared, okay? You don't need x plus 1 times x plus 1 squared, okay? You just need x plus 1 squared, right? Because this is the ultimate common denominator, right? Here you have x, but you don't have the x plus 1 squared, correct, right? So you multiply top and bottom by x plus 1 squared. This does not contribute to the common denominator, all right? Your common denominator for these 3 fractions is what? Yeah, your common denominator for these 3 fractions, though, is what? X times x plus 1 squared. It's not x times x plus 1 times x plus 1 squared, right? Okay, yeah. Yeah. Look, let me give you an example here. All right. Suppose you have denominators 2, right, 3, and 9. Okay. What is the least common denominator of those three fractions? What? 18, right, yeah. The LCD is, if we were adding those together, right, the least common denominator would be 18. It's not 2 times 3 times 9. It's not 54, right? Okay, it's just 2 times 9. Because 9 is 3 squared, correct? Okay. So, same thing here, right? This is the least common denominator for those three fractions. So this is missing the x plus 1 squared. So you're going to have to multiply top and bottom by x plus 1 squared, so that's going to give you in the numerator a times x plus 1 squared. All right, so let's write that down. We're going to have a times x plus 1 squared, right? What are we missing here? X times, and then another factor of x plus 1, right? So to add these fractions back together, I would have to multiply that into the top and the bottom. So the b is going to get multiplied times x times x plus 1. Okay. And then what's missing here? X, yeah, just the x, right? So the c and the denominator, but in particular the c is going to get multiplied by x, right? When you're adding those three fractions together. And so when you add the fractions together, you add their numerators, right? And that numerator has to add up to this. So that has to result in 5x squared plus 20x plus 6, okay? When we add these three fractions together, the common denominator is this. The numerators, though, will be this, this, and this. You add those numerators together, and you've got to end up with the 5x squared plus the 20x plus 6. So what I've got to figure out is what's the a, b, and c, right? So that these terms come together to give me 5x squared plus 20x plus 6, okay? I'm going to show you a couple of ways of thinking about this now. We learned a way before, but I'm going to show you a second way today that sometimes is necessary. All right, so what was the trick we used before to deduce what the a, b, and c are? Yeah, we picked a strategic x variable, right? Okay. Do you have any suggestions there, Cecil?
-1. Wait.
Yeah, -1 I think is good, right? Okay. Yeah. So if you put -1 in for x, correct? Okay. Because this expression has to be true for any values of x. So if you put in -1 for x, you'll get 0, 0 here, right? So those two terms will collapse. And you'll get what? C times -1 equals to something. Let's calculate what that is. So I would have C times a -1 is equal to 5 times a -1 squared plus 20 times a -1 plus 6. So that looks like minus C is equal to, what is that, 5? I just made it up, yeah. 5, well, I didn't just make it up, but I made it up. So what is that? 5 minus 20 plus 6 is that -9? So positive C is positive 9? So see, now we know what C is, right? Okay. So now we can fill that in. Because if I use +1, I'll end up with a bunch of A's, B's, and C's here, right? What I was hoping to do was eliminate either some of the A's and B's or the B's and C's so that I could deduce what one of the variables is. Well, the reason Cecil picked -1 is he realized when he plugged -1 in here, this would become 0 and this would become 0, and he would just get left with C, okay? That's the trick. Okay, Chris, now there's another another choice for X that would help us here. So I think another choice for X may be informative here. So we already used -1. What? Why 0? Yeah, this would cancel. This will cancel. And this is just going to be 1 squared, right? So now you're going to be able to figure out what A is, you see, because you don't have any A's, B's, and C's on this side. So let's try that. So if we let x be 0, well, you just told me this is going to be A times 1 squared, right? And then that disappears, is equal to, and what's 0 when you, what's this side when you plug 0 in for x? 6. So you see, now we know that A is equal to 6. Yay! All right. So that's very helpful. Now, there's really nothing I can substitute for x that's going to give me B, right? But that's okay. I don't need that anymore because now I know what A and C are. And now that I know what A and C are, I can use any value for x at all, okay? So I can plug in what I know A is, what I know C is, and then just don't make it -1 or 0, though, okay, right? Okay, plug in some other value for x, and then you'll be able to figure out what B is, right? What's a good choice there? 1, right, yeah, why make your life difficult, right? So you don't want to use pi, right, for x, right, okay? Plug in 1 for x, some easy thing to do, easy number to do calculations with. So I would get A, but A is 6 times 1 plus 1 squared plus B times 1 times 1 plus 1 not squared, right? And then C, but C was what, 9? Times 1, okay, right, is equal to, and what's on this side when you plug 1 in for x? What, 5, 20, 31? Got to be careful to add that up right. So what does that tell me there? How much is this? 24, right? 6 times 4. 2 squared is 4. Plus, is that 2b? Yeah. And then plus 9 is equal to 31. So it looks like 2b is equal to -2, which means there's a nice value. So b is -1. Yay. All right. So now that's really it, okay? Pretty much for this problem. So let's say I have 6 over x plus a -1 over x plus 1 plus a 9 over x plus 1 squared, right? But now I'm going to break these up into 3 integrals. And at the same time, let's factor out these numerators, okay? So I would have 6 times the antiderivative of 1 over x. Let's see, I'm going to factor out a -1, right? So I'd get -1 over x plus 1, and then factor out that 9. So plus 9 over, times 1 over x plus 1 squared. And now these are just a piece of cake, right? What's the antiderivative there? ln of x, right. So I have 6 times natural log of absolute value of x. This, what's that antiderivative? Yeah, ln of x plus 1, right? The derivative of x plus 1 is just 1, so you don't have to do any substitution there, right? You could, but you really don't have to. And this one now does require a little bit of work, right? Because that is the same as x plus 1 to the -2 power, right? So when we apply, this is x plus 1 to the -2 power. So when we apply the anti-power rule, right, looks like I'm going to get, what, 9 times x plus 1 to what power? Yeah, to the -1 power. And then all of that divided by -1, right? And don't forget your constant. So we have 6 times the natural log of x minus natural log of x plus 1. Let's see, how can I write this cool? Is that what? -9 over x plus 1 plus a constant? X plus 1 to the -1 power, that goes to the denominator. This is going to become -9, right? But that stays in the numerator. So, there it is. Okay. Wow. I'm impressed that we could integrate that ugly rational expression. Okay. So see, that's the power of partial fractions, but it did require that the denominator factor. Okay. So we had to be able to factor that denominator. So if the denominator had not factored, we really would have been in trouble. Okay, with that one. All right, so, the one key lesson to take from this example is when you have repeated factors like this, right? Repeated factors means you've got multiple factors, right? Multiple products. How should I put that? Okay. Well, I don't know. It's multiple factors, okay, that are the same, multiple identical factors, right? You have to take that into account with your in your partial fraction decomposition. So, what if this had been x squared? Yeah, and they would have been what? Yeah, x and then x squared. Yeah, that's right, yeah. Okay, so that would have been an even messier partial fraction decomposition. You would have had x and then a fraction with x squared in its denominator, right? Okay, and then the fraction with x plus 1, and then x plus 1 squared. What if that had been cubed? Yeah, not this squared, right, but just this cubed. I would have had to have written down fractions with what? X plus 1, x plus 1 squared, and then x plus 1 cubed in the denominator. But that wouldn't have been any harder to, may have been harder to find what the correct numerator is, but it wouldn't have been any harder to integrate because you would still use the anti-power rule, okay, to integrate it. Let me show you one more. This has one additional complication, okay? So this is really, the degree of this denominator is really 4, because if you expand this product, this square, you're going to get x squared squared, which is x to the 4th power. But I'm not going to expand that product, okay? I want to leave it in factored form. But the degree of the denominator is 4, and the degree of the numerator is 3. So we couldn't, for instance, use long division to try to integrate this, okay? But maybe we can do it with partial fractions, because notice the denominator is factored, okay? So we do have the denominator factored there. All right, so let's try to break that up into partial fractions, but now again, I have to think about what those partial fractions are going to look like, right? And see, notice here you have this factor squared, right? This factor is squared. By the way, x squared plus 2 does not, you cannot factor that any further, right? You can't break down x squared plus 2. All right, so what are my denominators going to look like there? X squared plus 2, right? Exactly. And then x squared plus 2 squared. Okay. All right. But now here's the additional complication in this example. What do the numerators look like? Yeah, well, you're thinking A and B, okay? Because every other example, we've had A and B. Unfortunately, it's a little bit worse than that, okay? Because you cannot factor this any further. What's the degree of that factor then? 2. So that means that we have to write down the denominator with degree 1 less. 1 less. So I'm sorry, not the denominator, but the numerator we have to write down with degree 1 less. Of course, what's 1 less than 2? 1. So I have to write down a degree 1 numerator. What does a degree 1 numerator look like? It's not just going to be a number. Numbers have degree 0. So what? It's going to have an x in it, right? Okay. So it's going to look like this, but plus, you have one additional possibility. There may be a constant added on. Okay. Huh? Because the factor here has degree 2, okay? So, not degree 1. So, in the partial fraction decomposition, the numerator, this is just the way partial fraction decompositions work. The partial fraction decomposition, the numerator in that must have degree 1. Degree 1. Yeah, it would be quadratic. It would be ax squared plus bx plus c. I don't think we have any examples like that, though. Okay, all right. Now, but look, let's compare that to our. So you might say, but let's compare that to our previous example here, right? What was the degree of our factors here? The factors, okay? What's this? A degree of this? 1. So the numerator can have degree what? 0. That's a constant. So see, this turned out to be a constant. This is degree what? 1. So the numerator can have degree 0. That's a constant. Don't say this is degree 2. This denominator is degree 2, but this is because you have x plus 1 squared. What is the degree of x plus 1? 1. So this can still be a constant. Okay? That can still be a constant. But if this were x squared plus 1 squared, this would be degree 1 then, which is exactly what we have in the next example. Well, the example that we're working on. So it is true altogether that denominator has degree 4 because x squared is squared. That would be x to the 4th power. But it's not the total degree that we're interested in. It's the degree of this factor that is squared. And again, that's degree 2, right? So this numerator must have degree 1. So that's going to be another linear numerator. So how am I going to write that down? I've already used a and b, right? So what? Cx plus d, something like that, right? Okay. Yes.
So why did we add b and c? Why didn't we leave it like...
this may turn out to be 0, and this may also turn out to be 0, but they don't have to be 0. If you have a constant here, this will still be degree 1. So it's possible you have a constant here, right? Okay. Yeah, it's like ax squared plus bx plus c, right? Okay. The degree is 2, but you can still have an x term and a constant term. So here the degree is 1, but you can still have a constant term. Constant terms have degree what? 0. Yeah, right? Okay. Yeah, so that's why you have to add that there. It may turn out that the b is 0, though. Maybe it just turns out to be 0. Okay.
So the exponent has to be attached to the coefficient.
The exponent has to be attached to the coefficient. I don't know what you're asking me.
To be cx plus d. Is that right?
No, it has to be a degree too.
Like with the x, right?
What now?
So there has to be an exponent with the x.
Well, there is an invisible exponent there, right? It's 1.
Like on the bottom.
Okay.
X plus 2 squared or something.
If it was x plus 2 squared, then it would be c plus d.
If it was x plus, what do you want me to write there?
If it was x plus 2 squared,
Oh, well, yeah, but x plus 2 squared is x plus 4, right?
it would be c, right?
That's right, because so even if you had x plus 4 squared here, okay, it would not be cx plus d, because this, the factor here that's being raised to the power, what's the degree of this? It's 1. in which case you would just need a constant here. So you could just drop the cx, right, and write down d. Yeah. Okay, well, all right, so let's see what happens here. I'm not sure. All right, so we're adding these together, right? And okay. So well, let's go off to the side then, right, and add them together and see what happens. So it's pretty easy to add them together, right, because this fraction is only missing one factor of x squared plus 2, right? So you're going to multiply the top and bottom by x squared plus 2. So the top would get multiplied by an additional x squared plus 2 to make this x squared plus 2 squared, right, if you were adding these two fractions together. So you get ax plus b, right, times x squared plus 2. Okay. All right. So that's that would be the numerator of this fraction if you were indeed adding these two fractions together. What's happening here, though? Fortunately, nothing. Right. Okay. So because that already has the correct denominator, right? So we just get cx plus d, and this has to add up to what? 8x cubed plus 13x. No, that's plus, right? Yeah, because we're going to add these two numerators together, right? If we think about adding, if we pretend that we're adding these two fractions together, we would add these two numerators. So this is addition. But this numerator, this fraction is missing that factor, so we would have to multiply that in to the top and bottom. Okay, wow, let's see what we can do here now. All right, so I'm going to show you now another way of trying to deduce. I'm going to show you another way now of trying to deduce what the A, B, in this case, the C and the D are. All right. I was going to show you this also in the previous example, but I forgot. But let's use it here. Okay. So the strategy that we have been employing so far, right, is to pick strategic values for x, and so that's a useful strategy, and you know you can try that whenever you like. Okay, but let me show you another thing that is also helpful, and you may have to mix these strategies sometimes. Okay, so what I'm going to do is I'm going to go ahead and expand this. Well, I'm just going to expand this product. Okay, expand this product, and then I'm going to add like terms together. Okay, so I'm going to go ahead and multiply these two things together, and then combine any like terms that I have. So in other words, I'm going to simplify the left-hand side here. The right-hand side, this is already simplified, right? You can't add those two terms together. But let's go ahead and simplify. So we have to multiply, these parentheses times these parentheses, right? So, wow, let's do that carefully. So I have ax times x squared. That's ax cubed, correct? And then I have ax times 2. So that's 2ax, I guess, right? And then I have b times x squared, so that's bx squared. And then I have b times 2, right? So that is 2b. And then nothing to do with the cx, right, or the d. Now, what are my like terms here? I don't have any more x cubed terms, so I don't have to do anything with that. I don't have any more x squared terms, right? So I don't have to do anything with these. So let's just write those down while I'm thinking about it. So this is equal to ax cubed plus bx squared. But now I do have multiple x terms, right? Because here I have 2ax and then I have cx. Those terms can be added together, right? Because you have apples plus apples. So how many x's do I have here altogether? 2a plus c, right. Okay, right? You have 2a plus c x's. So let's combine those. I have 2a plus c x's, right? That takes care of these terms. Now, what constants do I have? 2b and d, these are constants, right? So we'll group those together. Really no way to group those together other, I guess, just putting them in parentheses. So I have 2b plus d. And what's all this supposed to be equal to again? We kind of lost sight of. Yeah, this, right? It's got to be 8x cubed plus 13x. Now, all right, so look, this is going to give us a lot of help here, okay, already. Because we're going to now we're going to start figuring out what a, b, and c, and d are. Because, look, bx squared, you have that on the left-hand side. But what about x squared on the right-hand side here? You don't. So that means b has to be what? 0, right, okay? B has got to be 0. What?
Could we combine the x cubed from the right side?
Well, we're not going to combine it, but we're going to use it, all right? But this we now immediately know is 0, okay, right? So we know that b is 0. And a has to be 8, right, okay? Because how else are you going to get 8x cubed, right? There's only one x cubed term on this side. So a's just got to be 8. So a is 8. B is 0. That's useful to know. What about 2a plus c? What does that has to be equal to? Got to be 13, right? And what about 2b plus d? What does that got to turn out to be? 0, right? Because you don't have a constant here on the right-hand side, right? So this constant has to be 0. Oh, now you're in great shape, right? So what's everything equal to? D has to be 0, right? Because B we already knew was 0, right? So D also has to be 0, correct? So so we immediately know that D is 0. Oh, that's what I just told you, right? That these constants might be 0. So here's an example. So D is 0, and so I've got all three except C. Right, but A I know is 8, right? So you have 2 times 8 plus C has to be 13. So you immediately know that C is minus 3. Yay! That method, okay, is called acquainting coefficients for obvious reasons, right? We're going to collect terms on the left-hand side and then compare the same terms on the right-hand side, and the coefficients then have to be equal to each other, right? Okay? So A had to be 8. B had to be 0 because you don't have an x squared here, right? 2a plus c had to be 13. 2b plus d had to be 0, okay? And then use that system of equations that you get to try to figure out what a, b, c, and d are. Yeah?
How did we end up with b equals 0?
Because b we deduced was 0, right? And so that means then that, but 2b plus d is also 0. So since b is 0, d has got to also be 0. Otherwise, this won't come out to be 0, correct? Okay. So, well, so let's fill in. So this is nice. The b and the d are both 0, actually. So we end up with what? 8x over x squared plus 2. And then plus, d is 0 also, right? So it's minus 3x over x squared plus 2 squared, right? Now you see why we had to have the x's there, all right? Just constants would not have worked, all right? So that's why we needed the x's in our partial fraction decomposition. What now? Wait, say that now?
The derivative of the x squared plus 2 is 2x.
Oh yeah, but who cares, right? Okay, that's not going to be a problem. All right, so we're going to break this up, right? 8x over x squared plus 2. Yeah, I can pull out the 8. If I want to, I can pull out the minus 3, right? But now we will have to do both of those antiderivatives using substitution, correct? Well, I don't know. Maybe this one you can see, but it might be better to use substitution. What?
That one is derivative of this. You can just pull out the 8 and then x over x, so it will be 1 over u. So I have natural log of 8 natural log of 2 x squared.
Right. So that one is, you can do that one almost in your head, right? Okay. If you don't want to go through the whole full substitution steps. This one also really, you could also do without really, almost do it in your head without going through all of the full substitution. Yeah, it's just the same thing, right? Okay. So we can sort of kill two birds with one stone here, right? I am going to make a substitution, but in both cases, the substitution will be what? U is x squared plus 2, right? And so du dx is going to be just 2x, right? Which means what? Dx is, what's dx there? Du over 2x. All right, so I have here 8x over u, but dx is du over 2x, right? Okay. And now things are going to cancel nicely. Right here, I'm going to have, I should have factored out the minus 3, but I didn't. So we have minus 3x over x squared plus 2 squared, right? But that's going to be u, I'm sorry. So we have minus 3x over u squared. Minus 3x over u squared. Again, times dx, which is du over 2x, right? This is a square. So let's see, the x's cancel, 2 goes into 8, what, 4 times, right? So you can factor out the 4. So you get 1 over u du, right? Plus, and then here, let's see, the x's cancel again. What are we going to factor out? Negative 3 halves, so let me make this minus 3 halves. And then I end up with 1 over u squared, right? And now I'm in great shape. So I have 4 natural log of the absolute value of u minus 3 halves times something here. And how does that integrate?
That is 1 over negative.
Yeah, that's u to the minus 1 over minus 1, correct? Because this is u to the minus 2, and then plus the constant. So I have 4 natural log of u, which was x squared plus 2. So let me undo the substitution here. And what all happens here, right? That becomes what? Positive 3 halves. And then this is 1 over u, right? But u is x squared plus 2 plus the constant. So then really you're done, right? Okay. If you want to, you can write this as 2 times x squared plus 2, right? And then 3 in the numerator, but that's it. See, so that also was pretty tough, but we managed to integrate that, okay? So our integration skills are really getting very sophisticated at this point. Going to pay off handsomely for those people who are taking differential equations. All right. Okay, so that's my last example with partial fractions. See, these integration problems, right? The examples are so lengthy, right? Okay, so that's just the nature of the subject. All right. Yes.
For that, we're just using the like terms on the right hand.
Yeah, this is called acquainting coefficients. Yeah, right. Because you you simplify this expression. They should have the same terms in them, right? Okay, so you have to figure out what the coefficients on the left and right what the coefficients on the left have to be right to make them the same as the coefficients on the right. Yeah, okay. So the x cubed coefficient has to be the same as this. The x squared coefficient has to be the same as this. So it's 0, right? Okay. Well, there is an x squared coefficient. It's 0, right? Okay. And so on and so forth. Okay. All right. Let's take a break there because we got some heavy lifting to do. All right. So we're going to come back and talk about trig substitution. So it's not. What do I want to say? It's kind of formulaic. Trig substitution is, at least the initial steps are, but the simplification after you've made the substitutions can be challenging, okay? And the other difficult thing about trig substitution is we have to do 2 substitutions simultaneously. We have to do our normal U substitution. Typically, that's not too bad in these problems, but then we have to make a second substitution, which is the trig substitution. So we have this double substitution process going on, which also kind of makes it confusing. All right. Well, we'll see when we see some examples of what I'm talking about there. All right. So let's come back in a few minutes and we'll do that. Okay. Fortunately, they were kind of through with integration techniques. So if you can make it through this one, that'll be it. Not for integration, but for these different techniques. Okay, let's resume. One thing on the partial fraction homework. So maybe half of you have started on that. So do work on that before class next time. Do not try to wait until after class to do that, because I want you to come either to Taylor's session or to a class next time with whatever problems you have with that partial fraction homework, because I know there will be questions on that partial fraction homework. All right, so have worked on that so you have an opportunity to ask Taylor or myself, right, before it's too late, okay, to answer any questions that you have about that. All right, and the same here applies to trig substitution. With that homework, you want to make sure that you have worked on it prior to the last class before it's due, so that you can ask questions, okay? Because there are going to be questions from the homework about these problems, because these are lengthy. Okay. All right. So you remember, right, that we used inverse trig functions, correct? Right, to help us integrate certain types of expressions, okay? And I'm actually now going to show you how this formula is derived, okay? And in doing so, why is it that the antiderivative of an expression that looks like this, okay, how come that ends up involving arctangent, right? Because that's kind of a leap there, right, from this is just an algebraic expression to, wow, an expression that involves an inverse trig function, okay? So, see, there's a connection there between algebra and inverse trig functions. And so, how does that happen, okay? That's kind of surprising. All right, so I'm going to show you the technique that we use to pull off this integral, and then that technique, though, we're going to apply to other integrands, okay, as well. All right, so again, we want to prove that formula. So the antiderivative of, when you have the reciprocal of the sum of two squares, right, turns out to involve this arctangent. Okay. All right, so let's try to start on this, okay? So it's kind of squeezed in here, all right? It's kind of squeezed in here, but that's the problem that I'm working on, right? I'm trying to integrate that fraction, okay? All right, so here is the here's the game that I'm going to play, all right? And at first it seems like it's, kind of a very strange idea, but once you actually see it applied, you'll see why it's useful here. So we're going to we're going to use this equation, All right, we're going to use this equation to make a substitution. So this is called trig substitution, right? Okay, so there is going to be a substitution into the antiderivative, but a little bit different from the substitutions that we've used in the past, just a little bit different from the straightforward u substitution. Okay, all right, so this is the equation. This is the equation that I'm going to use to help me with the substitution. All right, so you just create this angle theta, this arbitrary angle theta here, and just assume that the tangent of theta is u from your antiderivative, right, divided by a from your antiderivative. Okay. Remember now, for this, remember to integrate this expression, right, using arctangent, we need sum of two squares here, right? So you have a constant squared, and then you have u, which could be an expression. It doesn't have to be just a plain variable, but it could be expression. But remember, it's this expression squared, correct? Now, I want to draw a picture, however. This is going to turn out to be important in the future in this problem. I want to draw a picture of this particular situation, where I have tangent of theta is equal to u over a, okay? We were doing exactly the same thing in pre-calculus this morning, all right? So, all right, so how do I draw a picture of this equation? Well, just set up a right triangle. So I'm going to draw a right triangle here, and I'm going to embed in there theta, and what this equation tells me is that the tangent of theta is u over a, right? Well, tangent is opposite over adjacent, right? So I'm going to, in this right triangle, I'm going to label the opposite side of theta as u, and the adjacent side as a, okay? And then, of course, then we just use the Pythagorean theorem, right, to deduce that the hypotenuse of this triangle is the square root of a squared plus u squared, all right? Okay, so square root of a squared plus u squared. So keep that in mind for future reference, all right? I'm just going to make a picture of this equation. We'll use it later. All right, now, but where does the substitution come about, okay, from this equation? Well, let's solve this equation for u, all right? So you do that, of course, just by multiplying both sides by a, right? Remember, a is a constant, right? Okay, u is the expression. So you get u is equal to a times tangent of theta. So we start with this equation to help us with the substitution. I'm going to draw a picture of that equation. I'm going to use that in the future in just a second here. But the basic substitution comes about by solving this equation for u, which you do easily, right, just by multiplying both sides by a. All right, so in place of u in my integrand, I'm going to substitute a times tangent of theta. That's the substitution. So I'm going to put in here a times tangent of theta. Now, I also have du in my integrand, okay? So I've got to also get rid of du, all right? So that means I have to differentiate this expression as well, all right? So I want to compute du d theta, all right? Well, let's see. Well, we just have to remember our trig derivatives, right? If u is a times the tangent of theta, what's the derivative of tangent of theta? Secant squared theta, right? Remember, this is just a constant. So du d theta is a secant squared theta, right? Which means if you solve for du, you just multiply both sides by d theta, correct? So you get du is a secant squared theta d theta. So that also has to be substituted. So I can get rid of that also has to be substituted so I can get rid of the du, right? Okay. That is trig substitution. Now, let's see what's going to happen here. So apparently something good is going to happen, but at this point, it doesn't look very promising, right? Okay, so du is a secant squared theta d theta, right? So see, notice I've changed the variable in the integrand from u to theta, okay? And what happens in the bottom here? Well, this is a tangent of theta squared, okay? Now, this is where the magic of trig, of course, is going to come into play, right? So let's see. In the top, I have a secant squared theta d theta, but in the bottom, when you square a tangent theta, you get a squared times tangent squared, correct, of theta. And notice from the denominator, from both of those terms, you can factor out an a squared, okay? So from these two terms, I'm going to factor out a squared. So what does that leave me with when I factor out a squared? Well, that's kind of obvious. I get a squared times 1 plus tangent squared theta. That's what I was looking for, okay? Because now there is a Pythagorean identity here that I can use to simplify 1 plus tangent squared theta. It is not the standard Pythagorean identity, right, that we're all familiar with, sine squared plus cosine squared equal 1. It's the second Pythagorean identity, right, okay, which is secant squared of x minus tan squared of x is equal to 1. But if you rewrite that, this tells you that what? 1 plus tan squared of x is equal to what? Secant squared. So here, I'm going to substitute secant squared of theta. Secant squared of theta here, because that's what 1 plus tangent squared of theta is. And now that is excellent, right? Substitution, because look what happens to my integrand when I make that substitution. This cancels. And we already were able to cancel a over a squared. I forgot to do that a moment ago. So that just results in a in the denominator. This is a constant, though, so you can factor it out. So, wow, look what happens. You get this very simple integrand, okay, from that original complicated expression. By this trig substitution, you get a very easy integral problem. It's just d theta. What's the integral of d theta? Theta. Right, okay, that's like integral of dx is x. Integral of d theta is just theta. Don't forget now you've got the constant in front, though. So you end up with 1 over a times theta plus, of course, you have to add your constant. So the integration is done at this point, okay? That is the antiderivative. But now what do we have to do? Yeah, we have to unsubstitute, right? Okay? So now we have to work backwards, okay, to figure out what theta is. Because we got to get back to what variable? No, what was the original variable in the integrand? I can't even see it up there. It was u, right, okay? So I have to undo my substitution so I get my expression, my answer here back involving u. Well, all right, so let's think back here to what substitution we made, right? Remember, we used what? Tangent of theta is equal to u over a. So how can you solve that equation for theta? Arctangent, right. Just take the arctangent of both sides. So guess what? You get theta is arctangent of u over a, okay? Theta is the arctangent of u over a. So now where I have theta in my answer, I just substitute arctangent of u over a. Oh, I didn't use my triangle yet. Darn it, okay? Well, don't worry, okay? That triangle's or triangles like that are going to be useful. There was a reason why I drew it. So there it is, right? Theta is arctangent of u over a, right? And so we just plug that in for theta. There's the formula, all right? So that formula you've been using successfully. I think you used it on test number 2, okay? I think almost everyone got that problem right that involved arctangent. Well, there's where that formula comes from, okay? By making that clever substitution, okay? So I don't know who was the first person to recognize that substitution, but it was ingenious, right? Okay, and it leads to this formula. Okay, all right, so we're not trying to recreate all these formulas because we've already used these formulas successfully, right? But we're going to use the same technique with different integrands, okay? So it will be very powerful in helping us integrate certain, or helping us find certain antiderivatives. So let me show you here a table that kind of summarizes there what substitutions you're going to make in different situations. And sometimes they work out nicely, and sometimes they don't work out so nicely. But they're things to attempt, okay? All right, so look, if you have an integral that involves, it doesn't have to be just this, but if it has this type of expression in it, then you might try making this substitution, okay? So for u, you would substitute a times sine of theta. So again, you got to have a square root there, right? And what's in the radicand here? What's under the square root? It's constant squared minus an expression squared, right? So if you have square root of constant squared minus an expression squared, then it can be helpful to make this substitution for u. Right, so keep in mind, if u is a times sine of theta, that means sine of theta is u over a. And if you draw a picture of that situation, here's what that equation looks like in a right triangle, right? Sine theta is, what's that, opposite? No, yeah, opposite over hypotenuse, right? Opposite over hypotenuse. So if we draw this right triangle, here's theta, I just put it in there. So the opposite would be u, and the hypotenuse would be a, and that means the adjacent side is going to turn out to be this square root, okay? A squared minus u squared, all right? All right, so if you run across an integral that involves this type of square root, then you can try this substitution, all right? Okay, now, that's difference, right, of two squares. What if we have sum of two squares, okay? Then the substitution you're going to use is tangent, okay? You're going to let u be a times the tangent of theta, which means tangent of theta is u over a, right? And if you draw a picture of this equation, this is the picture we drew just a moment ago. Here's what that equation looks like, right? Okay, tangent is opposite over adjacent. So we would label this side as u, this side is a, and then the hypotenuse becomes, notice the hypotenuse becomes the square root here, right? Now, here's the third case. Suppose you have this sort of square root, where you still, again, have difference of two squares, but it's the expression squared minus the constant squared. Notice this is the opposite. This is constant squared minus expression squared, but here we have expression squared minus constant squared. Then the substitution you're going to use is secant. All right, you're going to let u be a secant theta. Okay, yes. What now?
Don't you multiply the square root by u? Like isn't there u outside that?
No. Not for these trig substitutions. If you end up integrating with arc secant, right, then you need that, okay? But if you just if you just run across an integral that involves a square root of this type, you may try this substitution, okay? All right. So it doesn't. The rest of the integrand can look like almost anything, but if it involves this square root, type of square root, you can try this substitution, and that may simplify it, may not, okay, but it may simplify it. All right, so you're thinking of indeed you're thinking of this formula, right? You're thinking of this formula, correct? Okay. So if you have an integrand that exactly looks like this, then you know immediately what the antiderivative is, correct? Okay, but this trig substitution is a little bit more general. It just says, oh, if you have an antiderivative that has this type of square root in it, try making this substitution and see what happens. Okay. So the trig substitution technique is more general than this formula. U is not a constant. A is a constant. No, this is not a constant. This is an expression. Same as here. So look, so Heider, how did this formula come about? How must this formula have come about? How must this formula have been derived? What happened? Someone looked at this and said what? Oh, I have a square root, right? That has an expression squared minus a constant squared. So I'm going to try to integrate that by doing what? Making that substitution, correct? So they made that substitution, right? And they saw what happened, okay? It turned out that if you make that substitution and you also have the expression here, you'll end up with this as the antiderivative. But if you make that substitution and this expression is not here, I'm not sure what's going to happen, okay? All right? All right. So the trig these formulas are useful, but they're very specific, right? The integrands have to be put exactly into this format. But the trig substitution says I can use different types of integrals as long as they have this type of square root in it, right? Okay, I can try this substitution. All right. Well, here's the picture of the secant substitution. So I keep stressing the pictures, right? If u is a secant theta, then secant theta is u over a. But secant is what? That is, I forgot. It's the opposite of the cosine. Cosine is adjacent over hypotenuse, right? So secant is hypotenuse over adjacent. So you would put u here as the hypotenuse, adjacent as a, and then notice the opposite side turns out to be, by the Pythagorean theorem, turns out to be this radical, which is just that square root, right, that you're looking for. Okay. There are some conditions here on that one has to observe, but in practice, we usually don't think about those conditions that carefully until something goes wrong. All right. Wow. Okay, let's see if we can do this one. So this looks quite different than, well, it's different, not quite a bit different, but it's different from what we've tried before. All right. Okay, so first, what are you looking for? So what's your trigger here? Yeah, the trigger is that square root, and what's under the square root there? Yeah, you have difference of two squares, correct? Okay, and this difference of two squares is a constant squared, in this case 3, right, minus x squared, okay, right? So if you're thinking about that table said, if I run across that sort of radical, I may want to try a substitution involving what? Sine, right. See, that's constant squared minus u squared, okay? All right, however, I'm going to do a double substitution here because I want to change the variable x to u. Now, in this problem, that does not make much difference, okay? But in some problems, that initial substitution might be important, right? Okay? Because remember, in this table, the u can be any expression. So that could be a complicated expression here, right? Okay? In this example, it's not a complicated expression, but in other examples, that u could be a complicated expression. So I want to get into the habit of first substituting for x and changing the variable to u. All right? That's just a standard u substitution. So how are we going to change this to u? Just let u be what? X, right, okay? Just let u be x. Of course, the a here is a dead giveaway, right? A is 3, right? Because 9 is 3 squared. Okay, so, well, then du dx, of course, is 1. So easy here, right? That means what? Du is dx. So this is kind of a vacuous substitution. All we're doing is just rewriting the x's as u's in this case. So, but I want to make sure that I do that. So this is du. This is u squared, right, instead of x squared, because u is x. And then this is square root of, remember, a is 3, right? So you have 3 squared minus u squared, right? So, okay, so let's do that substitution first. And now we see, oh, we have a square root of difference of two squares. Bingo. That might be an opportunity for a trig substitution. And this is constant squared minus expression squared. So that is a substitution involving sine. So what was the substitution here? U is going to be what? A sine theta, right? A sine theta. So that's 3 sine theta. Okay? Now, you're going to have to, so you're going to replace u by 3 sine theta. You also have to replace du, though. So compute du d theta. So what's the derivative of u here? 3 cosine theta. Simple substitution, right? And actually then d theta. Well, no, I'm sorry. So if you solve just for du, you get, if you solve just for du, you get du is 3 cosine theta d theta. All right, now we're set to go, okay? So now we can make our second substitution. This is the trig substitution. So du is 3 cosine theta d theta, and then u squared is what? It's 3 sine theta squared, right? So 3 sine theta squared, and then square root of, right? Still the same thing, right? 3 squared minus, and then u squared is 3 sine theta squared. So now we've changed the variable for a second time. Now we have a variable involving theta, but now I'm hoping for some good things to happen here. Wow, let's see if some good things happen here. So what's going to happen right here? That's really the tricky part. So of course you have 3 squared, right? Which is 9. This also is 9. So I have 9 sine squared theta, and then square root of 9 minus 9 sine squared theta. But now underneath the radical, and this is this should always happen. This is why we chose this particular substitution. You can factor this 9, right? So you get 9 times 1 minus sine squared theta. But what is 1 minus sine squared theta? Cosine squared theta, right? So I get 3 cosine. This is supposed to have a theta in it that I keep dropping. So I have 3 cosine theta d theta over 9 sine squared theta square root of 9, and then this is cosine squared theta by the Pythagorean identity. Wow, didn't that work out beautifully? Because what is that square root? 3 cosine theta, correct? Which is going to cancel. Oh, just what I like to see are some cancellations. So this and this cancel each other. And I end up with still an antiderivative here, right? D theta over 9 sine squared theta. But that's the reciprocal of sine squared, right? If you want to, you can factor out the 1/9. And but what is the reciprocal of sine squared? May be better known as what? Close. Okay, yeah. What's the reciprocal of the sine? Isn't it cosecant? It's cosecant, right? So here you have cosecant squared theta d theta. So indeed, see, I have managed to simplify the integrand, okay, from what it originally looked like. But now that's not going to help me very much if I cannot integrate cosecant squared. But I think that's easy because what a trig function has derivative cosecant squared. Not tangent, but what? Cotangent. Okay, isn't it cotangent? What is the derivative of cotangent? Negative cosecant squared, right? Okay. Well, here I have cosecant squared, so it looks like my antiderivative would be. This is positive cosecant squared, so it looks like my antiderivative would be what? Negative 1/9 what? Cotangent there. Negative 1/9 cotangent of theta. So see, that turned out to be the cotangent. Sorry. See, that turned out to be surprisingly easy, right? Okay. Nope. Not your final answer. Okay. But we're getting there. The integral now is gone, so we have integrated. Okay. But how do we get back to the final answer? We have to undo the substitutions, right? Because we have to get back to what variable? What was the original variable here? X. So I have to undo my substitutions to get back to X. But y'all do see this, right? The derivative of cotangent is minus cosecant squared. Okay, and so so that's why we need this minus here, right? When we integrate. So so we ended up with a nice, easy antiderivative. Okay, now let's think about how in the world, how am I going to undo this substitution? All right. That's where I forgot to draw my picture, okay? But that's where the picture is going to come out to be helpful. So I neglected to do that right at the beginning, which is what I was stressing earlier. So now we have to backtrack and do that. Okay. All right. So remember, what was the key? What was the key substitution here? It was this, right? U is a sine theta, which means that sine theta is what? That's right. Sine theta is U over A. And what does that look like in a right triangle if sine of theta is U over A? So here's theta. So it's what? Over hypotenuse, right, okay? So I would label this right triangle with a U here and an A here. What does this adjacent side turn out to be by the Pythagorean theorem? Yeah, oh, by the way, the A is 3, right? In this picture, the A is 3, okay? So this is really 3. So what does this side turn out to be? It's always going to be your radical. So this is square root of 3 squared minus U squared, okay? Or 9 minus U squared, all right? You can find that from the Pythagorean theorem, but it turns out to be this square root, okay? Now, how is that helpful for me? Well, because what is it that I'm trying to figure out here, right? What is cotangent of theta? But in this picture, what is cotangent of theta? It's cosine over sine, but in this right triangle, it would be adjacent over opposite, right? Tangent is opposite over adjacent, so cotangent is adjacent over opposite, all right? So see, I know what the cotangent of theta is, right? Cotangent of theta is square root of 9 minus U squared, 3 squared is 9, right, over U. So we can undo this substitution. We get minus 1/9 times this square root of 9 minus U squared over U. Cool, right? Okay. Plus that constant. Now I have to get back to X. So, but what was a U? Just X. So that's an easy substitution to undo there. So we get minus 1/9. Well, let's write this as one big fraction. So I end up with minus the square root of 9 minus x squared over 9x plus a constant. There's my answer. All right. There's the antiderivative. Nice. Huh? This is hard? It's hard until you practice it a little bit, right? Okay, like all things, okay? Practice is how you learn. Okay. Actually, it's more than that, right? You learn what you practice, but you only learn what you practice. You only learn what you practice. All right, so, well, there's one example, okay? All right. Well, let's start another one. I don't know if we'll get through with it, okay? But let's try another one. Just again to remind us how things start, okay? So this one looks pretty innocent, all right? I just want to integrate the reciprocal of the square root of 4x squared plus 1. That almost looks like something we should be able to do already, but it's not quite. You won't be able to do it by a standard U substitution using the anti-power rule. You won't be able to use the anti-power rule here, okay? Because you don't have the derivative of 4x squared plus 1 multiplied in. If we had an 8x multiplied in, or even just the x, I would be in great shape, all right? I could just integrate that by standard U substitution. We cannot integrate this using our arctangent formula. Although the arctangent may come into play here, we cannot use integrate this using just the arctangent formula, because the arctangent formula requires you to have what in your denominator? It's just sum of two squares, not the square root of the sum of two squares, okay? So if this were just dx over 4x squared plus 1, you could integrate it using arctangent, just like you did on the test, okay? But the square root messes that up, okay? So the arctangent integration formula does not apply here, all right? But we're not at the end of our rope now, okay? Because now we have the square root of the sum of two squares, a very common occurring expression in algebra, okay? That occurs quite frequently. That's why it's helpful to be able to integrate it, okay? All right, so I can try a trig substitution here, and the trig substitution is going to be built on what? What trig function is going to help me here? Nope. Tangent, right? Because if we have the square root of the sum of two squares, tangent is that tangent substitution is the way to go. Okay, all right, and that's the situation we have here. But before I get started, I have to be a little bit patient. I'm going to have to make a standard, straightforward U substitution because I want this to be U squared plus a constant squared. This is already a constant squared, right? That is 1 squared. Okay, so we know the A here is what? 1. Yeah, our favorite A, right? Okay, but I first have to let U be what? 2x, right, okay? So that means that du dx is 2, which means that dx is du over 2. All right, so you cannot forget that, because that's going to change things a little bit here, because dx is du over 2. And then this is the square root of u squared plus 1 squared. Well, I don't want that 2 there, so how can I get rid of that? Put it outside, right, okay? So I have 1/2, and now I've got it like I want it, right? This now is ready for doing my trig substitution. And we said the trig substitution would be what? We're going to let u be what? A times tangent of theta, okay? So that's pretty easy. That's just tangent of theta. So I'm just going to substitute in here tangent of theta, okay? Well, I think that must be easy. Now, however, let's remind ourselves that if u is 1 times the tangent of theta, that means tangent of theta is u, right? Or u over 1. And what does that picture look like? So what's a picture of this equation? If this is theta, tangent is, no, it's opposite over adjacent, right? So the opposite is u, and the adjacent is 1. And so what's the hypotenuse here? Yeah, it comes out to be whatever this radical is. So it's u squared plus 1 squared, okay? Or u squared plus 1. So you may need that triangle later, okay? Where does the triangle become useful later? And I'm doing the substitutions right, okay? So that's why you have to write that down. Oh, all right, so here's where we are, okay? We have just now ready to make that substitution, okay? So we're going to plug in here tangent of theta, right? And I'm going to get tangent squared theta plus 1, and that sounds a lot like secant squared, right, okay? That's going to turn out to be secant squared, Wally, but you've got the square root of secant squared, which is secant. There I have the reciprocal of, so then I have 1 over the secant, but what is 1 over the secant? It's cosine, right? So this is really just cosine, okay? Right. An easy antiderivative, okay? All right, so that's where we're going next time when we finish this particular substitution problem, right? So we can already project, oh, this is going to be easy. This is going to simplify to cosine, and I know how to integrate cosine, right? Okay? And then I just have to undo my substitutions, and I'll have my original antiderivative, right? Okay? All right, so this is going to test a little bit your trig skills. So that's why I'm warning you, start working on this homework before it's due, before the last class where it's due, right? Because you need to ask questions. You're going to have questions. And Taylor will have a lot of expertise on this, okay? All right.